Okay, in this video we're going to look at resistive sensors. We're going to concentrate more on light sensors and temperature sensors, but start off first of all with our position sensor and look at our potentiometer. So our position sensor is a nice and easy one. We're going to connect up top and bottom of the potentiometer to our supply rails. In this case I've used 5 volts and 0 volts, and then it's this center point here with the arrow on. Now you must put the arrow on. This is our wiper, and it's this point here that we tap off the voltage, and that's going to connect to whatever we connect it to. So one of the inputs to an operational amplifier, or some other, maybe an analog to digital converter input or something. Anyway, so that's the voltage that's going to change. The voltage is going to change on our wiper position there as we move our potentiometer up and down. And I must say that our potentiometer comes in a rotary or in a linear. Okay, our potentiometer, it has a fixed resistance. Fixed resistance. Okay, this is different from using a variable resistor. I'll use a variable resistor when we look at our light or our temperature circuits. Okay. So we've got two configurations that we can have our temperature and light sensor circuits in. So there's our LDR here. Our LDR is at the top here. So our LDR, as the light level increases, so it gets brighter. Its resistance falls, which means here the output voltage will rise. There's our output there in the middle of our potential divider. Okay. So let's have a look at the other configuration where we put our LDR at the bottom. So on this configuration here, when it gets dark, the resistance of the LDR will increase. So as it gets darker, there's more voltage across the LDR than there is of this fixed resistor, so therefore the output voltage increases when it gets dark. Or you could say the output voltage decreases when it gets light, if you wanted to compare it back to this one. Okay, so we've got design flexibility about how we're connecting it to our circuit. So let's have a look at a couple of practical examples we could use with these circuits. Okay, so a nice easy one. We could replicate this. I could say what the resistance in dark is going to be and calculate the output voltage, but we'll just do the one where in its light the LDR resistance is 300 ohms. We've got a 1k fixed resistor here. So what is the output voltage? So it's just purely potential divider question. So I've just used the ratio method here. Gives me an answer of 6.9 volts. And if we'd done exactly the same question, maybe I said that the resistance of the LDR is 3k. When it's dark, what's the output voltage? You could work that out as well. Anybody do that? I make it 2.25 volts when it's dark if the LDR's resistance is 3k. I'm not going to do that, but I just wondered if anybody had a go. Okay, have another example. Okay, so this one we've reversed it around. So I'm saying that we've got 7 volts on our output here, and I want to know what the resistance of our LDR is at that point in time. Okay, so we're just using Ohm's law to work this out. So the first thing we can say then, well, okay, if there's going to be 7 volts across here, we've got 12 volt supply. So therefore, 12 minus 7 means that we've then got 5 volts across our 1k resistor. 5 volts across a known resistor size means we can then work out the current flowing through this resistor, which is going to be the same current flowing through our LDR. Okay. So 5 volts divided by our 1 kilo ohm resistor gives us 5 milliamps. So our LDR's resistance is just voltage divided by current. We've said that there's going to be 7 volts across it. It's got 5 milliamps flowing through it. Okay, that gives us a resistance of our LDR of 1.4 kilo ohms. Okay, that's straightforward. So we've got exactly the same two types of configuration for our temperature sensor. Our temperature sensor works in a similar way to our LDR. When the temperature rises, its resistance falls. Okay, so temperature rises, resistance falls. Okay, so we've got the two here. So on this first circuit here, as it gets hot, the output voltage will rise. And then in the second circuit here, as it gets cold, the output voltage will rise. Make a note of that. Okay. So again, we've got design flexibility with that. Okay, so let's have we'll just do one example with this because it works exactly the same way with doing the examples as we've just done with our light sensor. We'll just do one example. Okay, so on this example here, we know that we want an output voltage here of greater than 3 volts when the temperature falls below 5 degrees C. Okay, so we need to work out a value for R. Okay, so it's a similar scenario as before. If we know the voltage across our thermistor, so we know that this is going to be 3 volts or greater, and the values we've got is we know that it's at 2.9 K, and we therefore know what the current flowing through these two components is going to be. So I worked that out to be 1.03 milliamps. I'm going to keep that number in the calculator, so then if we can work out the value of R, we get a more precise value. Our value of R then, resistance is equal to voltage divided by current, so we're going to have that same 1.03 milliamps flowing through our value of R that's going to have then 2 volts across it. We can work that out. So 1.93 kilo ohms. Okay, one last thing just to wrap things up. I said I'd introduce a variable resistor into the circuit. Let's just see what that does for us. So popping a variable resistor into our circuit, what does it do for us? So we can replace our fixed resistor with a variable resistor. What does that mean we can do? Well, it means that we can then turn our variable resistor, which varies its resistance, but getting a value of 1.93 kilo ohms is going to be quite difficult. So what we can do then is we can use our variable resistor to allow us to finely tune our circuit so we can get the exact resistance we want, so we can get the exact output we want. So it allows us to finally adjust our circuits to get the output we require. Okay, and there you have it. That wraps this one up as well.